Hey everybody, when is the last time you saw a trig equation involving sine squared and cosine squared that doesn't use this identity, this unit circle identity? Let me write it down real quick. It's very well known that sine squared x, this is just the definition of the unit circle from an angular point of view, sine squared x plus cosine squared x is identically equal to 1. Okay. Now notice we're supposed to find a single positive real value here. And so we can re-express 6 cosine squared x is 6 minus 1 minus sine squared x. And that's easily, this is an identity, so if you subtract sine squared from both sides, you can see we can come from here to right here. Okay. Now, the part that made the thing fly actually is knowing to rewrite this like this. And this is due to the fact, very well-known result, laws of exponents, a to the m, the quotient of a to the m and a to the n. If you think of integers, it's a little bit different for real numbers, I guess. But if you think of integers, if you have m copies of a upstairs and n copies of a downstairs, and n is smaller, you get a cancellation, okay, to where n of these would factor with n up here, leaving with m minus n of them. Okay, so let's write that down. Okay. Again, easy to prove with natural numbers, not quite as easy to prove with real numbered exponents. Okay, and so you see, going from here to here is very clear, right? This would be 6 to the first, right? That's what makes it fly, 6 to the first. Okay. Now also notice that if we make this a substitution, we'll call it w, as you see. If we let w equal to 6 raised to the sine squared x, you can see it turns into something that's transformable to a quadratic. There we go. And folks, this is very straightforward right here. If you multiply through by w right here and collect like terms, you can get it in quadratic form. Notice that this factors nicely. So that you get w minus 3 times w minus 2 equals to 0. Now, let's take a look at what the problem actually asks us to do. We're only supposed to find a single positive real valued solution to this. There's multiple solutions due to the periodicity of sine and cosine, but it just says find an x that is positive, a real valued x that's positive, right? And so what I did is I just chose the value associated with w equals 3. W equals 3 is a solution, as is w is equal to 2. Okay, and I just arbitrarily picked w equals 3 right here. And you put a 3 right here, you get this statement, okay? Now, rewriting this logarithmically is towards getting everything algebraically isolated here. So you notice right here, this is just, if you take the natural log base 6 of this statement, okay, which is a solution to this, all right, you get this statement, all right? And the rest of it's just pretty straightforward algebra. Now, y'all notice you can do a change of base right here. Okay, you could write this as ln3 or common log if you want to over ln6. All right, and so, and after you take the square root, see here, I did quite a bit of the work for you here. I did use the calculator here, but all of these have power series representations, okay? Arcsin in particular, but this part right here, ln3 over ln6, is actually equal to approximately 0.783, okay? After you square root it, excuse me, after you square root it, all right? Now, also, just so you'll note here, there is a MaClaurin series or a Taylor series, I guess you could, for arcsin. So you could use calculus results to get this without using a calculator. I just used the calculator, but it's all doable as far as estimates with power series. Okay. So arcsin x is actually equal to this. And it takes some time, but you can actually see it gives you what the calculator returns. Close to what the calculator returns if you just do the first three terms here. You just do the first three terms, meaning put 0.783 here, here, and here. You get something very, very close to 0.9 radians. And by the way, folks, that is the answer. Now, y'all, this what I like about this. I get sick of all the nice answers. You know what I mean? Pi over 2, pi over 4, pi over 3. But this is not a nice angle. Not nice. All right. That's the stuff the kids memorize in school, you know. Pi over 6, pi over 4, and pi over 3. But here you just get flat out pi 9/10 of a radian. Now, folks, pi over 4 radians is about 0.78, I think. Okay, so this is something a little bit bigger than pi over 4 if you must know. But again, I did this sort of as a protest to places like Cybermath and all these places that do nothing but pi over 4, pi over 6, and pi over 3. So the 0.9 radians is one of the solutions right here. And again, you could put it right here. 6 raised to the 0.9 squared plus, 6 raised to the sine of 0.9 quantity squared, 6 raised to the cosine of 0.9 quantity squared is equal to very close to 5. You can actually check. And let me write it right here. X is approximately equal to 0.9 radians. 0.9 radians. Again, check it if you don't believe, but you get something real close, like 5.0000 and then some change, okay? So X approximately equal to 0.09, and that is our single solution that was asked for. There's actually 8 solutions to this, but I just wanted to show you the structure of doing this in a fashion where you can produce non-nice angles. Thank you.